All right, good afternoon, everyone, and welcome to the Packet Hacking Village and the new site of Speaker Workshops. Hopefully, this is a lot more open. You're more comfortable now than back there. Yeah. There's air in here, right? Okay, that's good. So now it's going to be Is it 3:10? Is it 3:10? I'm losing track of time. I mean, I've been out in Vegas for a long time now, you know. So you get to a point where you kind of lose track of everything. But our next talk is with. So wait, where are you from? Well, what company? Where you remember? Oh, you're from Splunk. Okay, yeah. So yes. So the next talk. You also I know you both also gave a talk at B-Sides Las Vegas as well too. So it is my pleasure now to introduce you Soto, Joseph Zadeh from Splunk, and give them a warm welcome.
Thank you. All right, thank you, Ming. So as he introduced us, I'm Rod Soto, and he's Joseph Zadeh from Splunk QBA. We work in the user behavior analytics department, and we're here today to talk to you about dynamic population discovery for lateral movement detection using machine learning. So it's been a busy week for us. We spoke at B-Sides, we spoke at Black Hat, and today we're speaking here. What we did is basically we've been doing a lot of research in regards to user behavior analytics in several areas or entities or domains, if you call it so. So there's plenty of research. We divided it in 3 areas. And one of the things that we did at Black Hat, we released an open source machine learning tool where you can actually apply it to PCAPs, and it will tell you if there is an exploit chain and a risk score for ransomware. Maybe we'll talk a little bit at the end, but we will be releasing the tool is already up, right? Okay. Okay, so I believe I introduced myself already. I've been with Splunk over a year already. Was part of the Caspita acquisition, which was a startup in machine learning user behavior analytics. And Joe works with me on the data science department. So let's get started. So what is lateral movement? We define lateral movement as a series of actions conducted after a successful exploitation attack or infiltration in an organization's network that seeks to further reconnaissance and expand reach of attacker by gaining knowledge of internal network assets and obviously accessing them. So here's a diagram of a sort of like a workflow of how you can visualize lateral movement where you have a server outside the edge. This server, let's say, has a RFI, remote file inclusion. Preferably if it's PHP, you can basically maybe get an RFI exploit, upload a web shell, a C99, BTEC, R57, whatever your flavor of web shell is, and then from there we can pivot. And there are very nice tools that can be used to further post-exploitation. For example, with web shells, I don't know if you guys have used Wibbly. It's a wonderful tool. And it is very interesting to use when you have limitations on the size of the shell that you can upload to certain vulnerable servers. So once I'm in or I'm able to access or get a hold of a server with a web shell, obviously what I want is to further my actions inside of a network. And then if there is a possibility of accessing internal servers and then moving laterally by mainly either escalating privileges or getting a hold of passwords, then now I can move around the organization and then obviously get what I want. It will depend on what the objective of the malicious actor is, but that's pretty much the main concept. So, as I said before, you have here an example of lateral movement, and then obviously there are several tools that you can use, and then really conduct lateral movement and either exfiltrate information or just monitor or basically create persistence and then further your stay at that host network. So obviously you want to gain further knowledge about internal network access and you want to expand into other systems. Like I said before, the goals can be different depending on what you're targeting, but basically what you want is to get the crown jewels. If you have like domain admin account, that's it, it's game over. That's pretty much it. Once I have an enterprise domain administration account, that's pretty much it. I can do whatever I want. And here are some of the tools that we have seen and we use ourselves. I'm myself a pen tester. So why is this important? Well, the main issue here, and if you guys have been, for example, looking at the Verizon report, the concept of dwelling, right, or detection deficit, how Verizon calls it, is basically how long does it take for an enterprise to discover that they have been breached, have been penetrated, and the longest, obviously, it takes for them to discover them, the worst for anybody. So that's why lateral movement is important. Because there are times, I'll tell you, I'll give you an example. We were playing with an algorithm, and I was using a encrypted payload. I was just using a outbound 443. So for example, if you have like a PAN device, they won't see it. However, when I pass the hash and I RDP into one of the workstation, I got an alert saying, this guy never RDP to this workstation. Lateral movement. And that's how the algorithm caught me. So this is why it's important. Sometimes, you know, if we're looking at things at the edge, sometimes we cannot see it, but if we look at the patterns of behavior and indicators that sometimes we really do not pay attention, or because we get so much information, we can't just see it or grab it at the right time, then we can discover things that right now is very hard to see. So obviously, if we want to improve detection, and in this ergo will reduce and contain for an impact, and obviously detection or lateral move enables SOC, SecOps, IR, DR, depends on what team you work at, to act in a more efficient manner and coordinated manner, and obviously increases the cost and deters attackers, and would be external attackers as well as insiders. This has been said forever. The higher the cost for an attacker, unless you have, I don't know, something that's very valuable, or it's a nation state that is determined to get you, usually the higher, the more difficult that you make it to be compromised, it's likely that low to medium level attackers will walk away, plain and simple. So how we establish assets, right? Because we're looking at lateral move and at dynamic discovery. So basically we need to define what is an asset. So an asset is and I took this as a generic from Wikipedia, it's basically a data, device, or other component in an environment that supports information-related activities, right? So this can be generic, and sometimes the reason it's generic is because when you're dealing with user behavior analytics, you have to be ready to deal with disparity and diversity of sources. So one of the biggest challenges when processing information and applying algorithms to it is what we call ETL. You guys are familiar with what ETL is? Extract, transform, load. It's a big data term. So basically we have a CEF format, but then we have a CSV format, but then we have an XML format. So all of this needs to be parsed and injected and then processed by the algorithms. And this is a challenge. And because we're trying to look at things that are usually not static based, which is also one of the advantages of using machine learning, you can teach algorithms to find patterns and to define micro behaviors that are otherwise non-present and static signature-based technologies such as antivirus, such as endpoint, such as firewalls, IDS, etc. You can complement it though. Machine learning is not a panacea. It's not going to solve everything in one shot. However, it's an enhancer when it comes to detect and prevent. So obviously, this comes back to things such as why do we had to pay attention, lateral move, asset management, and define our assets. Obviously, if there is no asset management, there's no risk analysis. If you don't supervise or you don't monitor well your assets, you're likely to be targeted and exploited by attackers. Ever heard of shadow IT? Anybody shadow IT? You ever heard of it? Excellent, right? People bring in their own routers, Windows XP computers from home, all right? So if you don't know what you have in your network, what you don't know can and will hurt you. So this is why it's important to know what we're dealing with, how we manage this, and how we approach it. Obviously, this is needless to say, but I have to repeat it. The lack of OS application version patch level obviously increases the risk of compromise. If you don't know, sometimes I know there are decisions in enterprises that are made on, okay, if we have seen, for example, in the field, a certain patch crashes, Microsoft Windows software, have you ever heard of that? Is that like rare? So sometimes, and me as a sysadmin, I say, I'm not patching that. Well, because, you know, if I can't come back, my server doesn't come back, then I'm now legally responsible and legally liable. However, this has to be approached, it has to be managed, obviously. But the lack of management of batch versions and OS versions, obviously, is a huge risk. Not only because you are exposing yourself, but because even attempting to fix it, it might be a problem. Enables the access management of resources inside the perimeter, which is what we're going to talk about. We saw that in the example that we saw, the exploitation started from the edge. However, we're going to focus on the perimeter. And then finally, obviously, I'm assuming I'm with a lot of security people here. It enables SecOps, IR, DS, disaster recovery, incident response to identify access to resources in cases of an incident. How many pen testers do we have here? Raise your hand. All right. Anytime you submit a report to SecOps, what do they tell you? Prove it, right? I'm not touching that firewall until you prove it, right? So it's a fight, and it's a fight. I went through that. I had to deal with developer teams, which they were awesome, but every time I showed them proof of something that was potentially at risk, and I would show the exploit, actually the proof of concept. It was a fight, and sometimes change management works against you, where you had to prove beyond any reasonable doubt that this system is at risk. So asset management definitely helps you in that fight. And with that, I'm going to leave you with Joe. He's going to talk at practical machine learning for security.
Thanks, Rod. Can you guys hear me okay? Okay. So just to kind of start to deep dive into some of like the math and the kind of motivation here, part of what we were doing and kind of exposing is this. Essentially, we put a paper together for our machine learning conference called KDD. I mean, it's sort of like the abstract is up here. It's super academic. It's really dense. But if anyone's interested in sort of like the white paper, come see us afterward, and we'll forward you some of the kind of the theoretical ideas that are sort of underlying what we're going to be talking about. But basically, at a high level, one of the challenges we try to help solve and help large SOC solve at scale is taking some additional signal from the data within the enterprise, and this gets abused a lot. Like I think in sort of modern kind of marketing terminology, where we see machine learning applied all over the place in security, and from our perspective, it's we want to be really practical about where we're using it and where we get value from it. And And there's been some really cool talks. Like the talk right before here, I think was an awesome, like sort of creative application of machine learning and offense. But anyway, I'll kind of just deep dive with you a little bit on where we kind of see the nuances here play out and how we try to be practical about it. But at the end of the day, we're kind of applying a methodology to attacking some use cases, essentially. Like, we'll get to a really large customer. The model I will be shown here kind of was motivated out of a lot of like what Rod was calling like the shadow IT problem, and particularly in healthcare. So with large hospitals, we would kind of be dealing with sort of this problem of biomedical devices being plugged in that have to go through this like FDA patching approval process, and oftentimes they'll get like whole families of these like devices that are like Windows XP enabled, they're not patched properly, and sometimes the asset management systems won't even know about them. So like one thing we can do is just try to learn profiles of these assets and say, oh wow, I look like you know, in this way we're able to kind of distinguish between like an HVAC controller, like a hospital bed, you know, just a Windows phone and like a web server. So that's kind of like the high level motivation. But at the end of the day, like these machine learning models and stuff, they don't, like if we just stuck this one model out in the world and deployed it at a customer, it wouldn't bring a lot of value. The power with some of these solutions is enumerating the threat surface. So that's kind of what we're talking about here, is taking a bunch of different use cases and mapping them to existing point solutions, knowing what our SOC's capability is, and maybe augmenting some of those use cases that we think are going to have like additional value or additional signal derived with a kind of an analytic or a data-driven workflow. I'm just going to jump ahead here. And I think kind of to touch on sort of these kind of practical considerations with machine learning, there's something really just that's sort of a natural part of doing security, and that's what we call kind of adversarial drift, in the sense that if I train I've seen this happen in my own sort of just kind of research. Like I used to help build a lot of models for covert channel detection for detecting when like maybe a few years ago, it would be like when HTRAN is doing some kind of like phone home or command and control. And part of the assumption with some of these rats we were hunting for a few years ago was that they were going to be persistent on a file system. So, you know, they were an implant on someone's computer, and they were going to have callback at some point. I think like that shift in adversary behavior from back then to in-memory malware means we can't even hunt for artifacts on the file system anymore, much less like have a dependent sort of beaconing profile in the network traffic. So it's these things that these shifting behaviors that make any kind of automation brittle, because when we train something, when we have a model learn a profile of an attack behavior, all it takes is the attacker to change some aspects of that behavior for us to force our machine learning algorithms to relearn. And so that's why it's sort of one of my favorite kind of like slides especially when I sort of talk to like just bigger defensive conversations where we're talking about what does it mean to you know mature your security posture. Like oftentimes when we see kind of sort of mature intelligence operations mixing with the machine learning, where there's a manual, you know, just tier 2, tier 3 kind of escalation personnel that are able to handle triage and do some of the manual work that is almost impossible to automate. There's this sort of like, if you break down models of the adversary, we sort of see like there's a couple of models of the adversary where we're basically assuming the adversary has a lot of resources, and in that case, it's not such a good problem to necessarily like punt to a machine learning analytic. So if we're talking about APT or you know just an adversary with motivation and lots of resources, then the security posture sort of has to be driven by some of these, you know, just lots of different kinds of solutions, like deep packet inspection, you know, augmenting all these things to even attempt to attack this problem. And so just one last kind of consideration here in terms of like maybe to hit home about being really practical about this is sort of what we're going to be kind of showing from an algorithmic perspective is what happens when we learn. And this is sort of a universal principle. It doesn't matter if we're talking about an algorithm or a human being or like a dog. It's all the same, because because essentially when we learn something, we're sort of taking hashes of the information. And this, like if you're kind of go really deep into like the research literature, like this, or if you went to like a machine learning class, this might be referred to as the formal concept as VC dimension. But in some sense, it's just, there's an intuition here. So I'll just kind of like run through the intuition. So just take a model, like, or sorry, I've taken a data set, you know, has maybe 1,000 rows, right? It's in a table somewhere. In this case, I grabbed it from this open source library or package called R. And then I fitted, sorry, I skipped ahead one step. So I fitted basically a linear regression. I just trained a line basically on 3 variables. We're making an assumption in this model that miles per gallon in the data set is sort of linearly dependent in some way on weight, displacement, and the number of cylinders in a car. So it's just a super toy example to show you sort of what happens when we take a bunch of input data, in this case like 1,000 rows of car information. We basically pass it through an algorithm. In this case, it's sort of the simplest learning algorithm we learn in school. It's called a regression. And then the output of this, what we learned, is sort of a hash of the data. In this case, it's just I mean, there's more here than just the coefficients, but in some essence, the learning is captured by these 4 points, these 4 coefficients. And this sort of illustrates the learning compression duality. And so why is that important? Well, it shows us that these systems are brittle in this sense. Like an analytic becomes a hash of information. So it's never gonna be as good as the original information in some sense, but also we can use it in sort of lightweight lookup tables. You know, like I do lots of this for like what Rod mentioned. This project we just put on GitHub is we basically trained a little model on the delivery of an exploit in HTTP files, and we had about 400 samples of exploits being landed in these sequences, and we had the model learn sort of the hash of what that looks like. So now when I get another sequence of HTTP requests, I just do that like kind of a hash lookup, and in that case it's useful as sort of an augmentation in different sort of workflows. So yeah, if you're interested in the GitHub project, like basically we're leveraging just this sort of a classic machine learning kind of classifier called a random forest. So I can kind of deep dive with you. Just come talk to me afterward if you want to get links or get the code or anything. And then yeah, so kind of tying back to the brittleness of this kind of learning process. So when we actually engineer a learning system for security, we have to deal with these two problems. One, that the attacker's patterns will change over time. So what does that mean to really, when have I learned good enough? Or when am I done learning? Or when do I need to stop and forget? And so we have to like implement a whole API, and basically whenever I write a model to deal with sort of a use case, I have to sort of think about this. I mean, this is sort of a dense slide, but there's a whole workflow that's about like automating and engineering the concept of relearning, what does it mean to forget, and how do I apply it to a particular use case. And so these all become just nuances for some of this, you know, like how far we can go with machine learning as sort of a tool in security. And I think also kind of the other thing, just more from like a security offense versus defense perspective, is I would even if you're sort of on more of an offensive side, or particularly for just like an adversary, if I were to be attacking kind of modern enterprises, one of the things that probably is important to start game planning against and expecting is these sort of non-deterministic solutions that are starting to be exposed in different workflows. Really at the top Fortune 10s and 500s of the world right now, I'd say you probably have to worry about a system like this, kind of hunting for footprints. These kind of sort of data-driven like views of the world are going to become more and more common, and so to attack like a sophisticated kind of shop, you might want to think about really in regards to like some of these things we're highlighting is attacking the logging sources first, you know, and being careful about where you can be discovered in some of these data-driven kind of scenarios. Oh, sorry. So just kind of like really quick to just now walk you through sort of some of the the key outputs and inputs of this analytic we're talking about for detecting lateral movement detection. And the end of the day is we're going to basically try and use enough data to sort of assign some color to a social network. So we take a bunch of data from like network traffic, from pretty much anything that we can get in the enterprise that has like things like source IPs, MAC addresses, like I'll kind of walk you through it. And then what we'll do is we'll build like a graph of this data set, and we'll evolve this graph over time. And what we can start doing is like color coding the graph. For one, once I get a really big network graph, sometimes it's even hard to identify the web servers if we don't have like a Visio spreadsheet or like an asset inventory person to kind of manually label them for us. So here, what we're doing is we're having an algorithm learn which things look most like the perimeter web servers, which things look most like the kind of inline IPS, which things look most like domain controllers, which things look most like hosts. And once we know that, this is sort of the power of blending many models together. We pass that sort of the output of this model to another model. And so in one case, whenever I've labeled all the web servers, what we start doing is any one of those things we've labeled as a potential web server, we start monitoring with another analytic that's looking specifically for web shell behavior on each of those web servers. And this is sort of the way we combine and treat all these sort of models as first-class citizens, where the real power is putting many of them together. And so just kind of like walking through the algorithm workflow now, basically the key kind of step that I've spent, every time I've worked on one of these problems at large scale, basically I've spent like 2 months of the problem working on identity resolution. And this could get really complicated, or you could do some sort of tricks to keep it simple. But part of the workflow I'll describe to you that I think will always be there in some sense is step one. And then kind of the next few steps are definitely sort of custom to how we've implemented it. But in some sense, we just have this, from an algorithm workflow, we kind of break the problem down into a few key steps, and we sort of automate this as an ongoing job. And we could kind of think of like how this is sort of represented a little bit in kind of like individual modules of code is kind of like this workflow. And what we're doing under the hood here is leveraging, like, sometimes we'll have to do this on, maybe one of the bigger networks I've been on is like 350,000 hosts, and what does that mean to have a heterogeneous traffic profile for each host? And then, so it becomes a really kind of expensive computational problem, and a problem we want to parallelize in smart ways. So right now, under the hood, we leverage a lot of these kind of workflows through some Apache projects called Spark and MLlib. And at the end of the day, like, kind of what's sort of interesting about the analytic is it gives us, like, once we see, so one way to like hunt for pass the hash or pass the ticket, for instance, is to like, to have visibility onto the host, to do all these, to do all these tricks that are sort of file system specific, and just analyzing kind of the network traffic for some kind of weird games that are played with Kerberos when we see the pass the ticket attacks. But another thing you can do in some sense is sort of like at the bottom of our output here, which is kind of what we create as anomalies. And so when we've identified what profiles of humans are basically attached to IP addresses, we can say, oh, this IP has 99% of the time it's driven by a human activity. It's driven by sort of an end user behavior. Whereas like this IP over here, it only does MS update. It's only talked to 2 domains in its whole history of its traffic. It has a very specific profile that looks like a server. So now that I know these 2 facts, I can basically start coloring the edges so that when we see like pass the hash and pass the ticket, we see sort of like non-standard directions in the edges of this graph. And so that's it's probably not that clear here, but that's sort of what we're outputting in terms of anomalies at the end of the day in this very last step of the workflow. And kind of like, so here's sort of like visualizing the algorithm in action. This is, I wish I could be like a better analytic, but anyway, this is basically done with something called Gephi. So it's just, so basically we take a graph network traffic. I've taken like Palo Alto data in this case, proxy data, maybe like NetFlow too, just a couple data sets for a large enterprise. I think this might be like 50,000 hosts. And then what we sort of do, it's not going to be really clear here what the colors correspond to or anything like that. But basically, there's sort of the next step of the algorithm is just doing some analysis, some enrichment, and identifying different sort of asset classes. And finally, we're able to detect, and then we sort of evolve this over time. And we're able to detect, basically, when like a web shell or like a server all of a sudden created, like in the perimeter, created a path that we've never seen before across maybe some different parts of the topology in the network. And so yeah, so that's sort of just the analytic in action at a high level. One of the most sort of fundamental things for any of these workflows, and pretty much a big portion of any of these large-scale kind of analytic security solutions I've worked on, this is really where I think that this is sort of a make it or break it kind of thing, because if you don't get identity resolution right, then you're not able to make like stable baselines over time, especially because of DHCP churn. So, and one thing, just on the topic of identity resolution, there's this pretty cool Usenix paper that came out called Beyond Corp. If you guys aren't aware of it and you're sort of interested in this topic, I would definitely check it out because Google's doing some really, sort of kind of heavy-duty kind of ways to rethink what it means to maintain identity in an environment. And so if you sort of want to see under the hood how these things manifest, typically like we'll take lots of different data sets, and then what we have to do in some sense is like evolve, like how do I show you? Yeah, maybe this is the best. Like basically, we have to sort of evolve a kind of like a time series of users and kind of their state change for certain things like MAC addresses, IPs, host names. And then this becomes basically like a little bit of an expensive lookup because you're sort of always doing like a range query against a single point in time. But if you create a job out of this and maintain this logic, what you're able to do is sort of have like a model, like our model kind of subscribes to this table at the bottom that's basically like just a normalized union of a bunch of pieces of information about an individual user. And we're constantly updating this. And I've seen this get really sophisticated for the use case of like monitoring for VPN kind of compromises at the perimeter. I've seen places where they even build like a probabilistic match on the user based off their user agent strings. They use most common, like a bunch of little like heuristic indicators to even make probabilistic identity resolution. So there's different levels you can take this to, but for sure kind of just doing a vanilla correlation against ranges in time gives you the ability to replace an IP by a MAC address or something much more stable. And then we can start to ask the question like, is this a normal access pattern for this asset today? So that's step one. We do this topology discovery or identity resolution, and then step two is sort of this overlaying the colors and basically some intuition behind like the OSI model. And this is so this is the one caveat with doing all this stuff, and this is sort of like one of the biggest sort of challenges in security in general is just sort of having visibility into the lower layer thing. So when we're talking about monitoring network traffic, right? Like one of the biggest things that happens is, when we are landing data in a SEM, we never land switch flows. You can't land like all the traffic that happened in a stack. It's just way too expensive. So you don't see like the layer two, the lower layer information in any kind of network monitoring usually at scale. You can't log PCAPs at scale. You can't log the switch traffic. You can log the routed traffic. And so the fact that once we get to really large networks and they become part of the environment, we lose visibility because it's mainly switched. That's just a visibility issue that has to be solved for in other ways, either having kind of endpoint visibility into the host through agents. And that's sort of one of the biggest challenges I see these sort of shops dealing with at scale. But at the end of the day, we take this intuition, we overlay some different things. Like in this case, for every IP, basically we build sort of like this idea of what's going on in the topology. Is the IP in the LAN, the DMZ, or is it sort of external to the enterprise network? And we can add, essentially we could add a bunch of like different statistics to each IP or each MAC address. And that's kind of the key idea here is we're basically building a bunch of these little tables. Once we can identify the host by a MAC or something stable, then I can ask like how many times do they talk to, how many times a day do they talk to the perimeter? How many times a day do they talk to like a Facebook domain? And in this way, it's pretty simple. Like you could just, once you start building the distribution of each host's like just outbound web requests, it's really easy to identify. I mean, with the exception of sort of VMs and kind of multi-tenant hosts, you start to see like when everyone kind of connects to Facebook and Yahoo and checks their mail every day, it's a population that looks completely different than the server population, which has like a much smaller cardinality in the number of hosts like they talk to. Like all these facts like kind of let us sort of segment these different groups. And so some of these slides that are on here came from like a sort of a PhD statistics presentation, like one of our interns. So there's going to be a lot of statistics things in here that are like you can just kind of ignore. But basically. If you really want to go deep into the math, come see me afterward. I'll share you some of the other notes that have a little bit more of the stat stuff in it. And then so here's sort of like the high level goal of like actually like taking an analytic and labeling things in the environment. I mean, from a lateral movement perspective, the first thing we tried to get really good at was just saying like automatically saying, okay, when this IP or MAC address has a user behind it. Like just tell me yes or no, and from there I can pass that information upstream to sort of other detection techniques, and I think kind of so the key things to identify for us really from kind of an initial POC perspective was like just like the types of end user hardware we might be seeing like kind of desktops. Host type and kind of mobile iOS type devices, that sort of thing, sort of tied to the end user population. And then the other key kind of population to sort of just get really good at identifying is servers and hardware, particularly like in the DMZ, really being good at identifying any web servers, just types of things that are kind of perimeter exposed, as well as kind of some of the more challenging IoT type devices. Particularly in healthcare, we would have bunches of problems with having ways to find the biomed devices and sort of the shadow IT problem. So what does this profile look like? I kind of talked about building a distribution over like for example, for every server you look at, if you kind of start asking what are the outbound IPs, oftentimes you'll see with the server population, it's a much kind of smaller of a communication profile than a human. And what's more important is like you can kind of map things to like updates and some of these different sort of key sort of invariant maintenance workflows that kind of give you a little bit of signal. But it takes a lot of work, and so what we do is we sort of break down a profile. I mean, in terms of machine learning terms or kind of statistics, we have to build like a whole feature vector of information. And a lot of these are just kind of like the example I showed earlier, which is just like a couple of statistics we compute about the number of outbound versus inbound connections and stuff like that. And so then now we add the time dimension into this, and basically we build, so the identity resolution step lets us sort of maintain this time dimension in a way that now we can be robust and maintain both baselines and sort of compare a profile for an asset today, tomorrow, so on and so forth the next day, and basically an infinitely running job. And this way, this is sort of the classic idea of creating a baseline and what's sort of interesting when you start doing these things and you see sort of like some of the power here is maybe even like falling back to a default case. So one of the classic questions we get asked is like, okay, like I created a baseline, I have maybe a whole OU, a whole peer group of like the sales organization, and now you get a new guy in sales today. So like, how do I know if what his actions are good or bad if it's the first day? And often, and so from an analytic perspective, you really can't do anything unless you fall back to his peer group. And in this way, sometimes even if we don't have baseline information, as long as we have information for his neighbors, his peers, we can kind of overlay that and use that as the default until we get enough signal from the new individual. And that's sort of the power of the data-driven approach here is these little kind of tricks like that. And then there's a lot of different sort of things that goes into a profile. I think kind of what's common across lots of environments I've found is, well, what's really nice actually is if there's Palo Altos and there's sort of nice visibility maybe in across data centers, then we can kind of get a really nice, even LAN to LAN, private to private application fingerprints. And basically, if you build an application fingerprint, so the Palo Altos will give you, for each network traffic, there's a field that will give you sort of the app they kind of fingerprint in the traffic, or they think what it is. I mean, oftentimes encrypted traffic isn't so helpful here, but basically you'll get a distribution of each sort of application that is used by a single host. And like servers stand out, like, let me see, I think, yeah, this is probably an end user. We see some iCloud, Gmail, iTunes, but servers stand out so much. Just here's the application distribution of like a domain controller. And it's just this, it's sort of a smaller cardinality. It's really easy to sort of spot once you kind of build up all these calculations. And here's sort of where the kind of machine learning comes in. We do have sort of this whole workflow, and basically we have to have the this is sort of like statistics problems. Is now how do we compare like different features, different profiles, and how do we compare them across time? So we sort of had to implement a little engine to sort of cover these use cases. And then kind of the final thing we do is sort of a higher level. So we kind of do the sort of lower layer kind of like graph-centric analysis in the first step. And then what I mean by the OSI model is kind of we go up to the sort of application layer now, and we start talking about there's just sort of a bunch of different examples in here. I guess I could kind of, since we're running low on time, I'll just, hopefully you guys get a sense of, we basically compute a bunch of different profiles at different, based off different logs we have essentially. And then once we kind of get those profiles, this is like the magic anomaly step, is we're able to kind of build like this time sensitive analysis of, this server actually talked to a LAN asset, and this server never even initiates connections to hosts before, or vice versa, So kind of building these really graph-centric indicators lets us, like, for instance, the web shell is my favorite kind of example to cover. Is like once an asset in the perimeter gets popped, oftentimes its behavior, its communication profile will change a little in terms of what it talks to next, or what. So to give off these little signals, aside from just monitoring the behavior of the file system, like just hunting each web, like the whole time we want to be watching, as long as we know a web server is online, we want to make sure, are there any new kind of URIs that shown up that only one person talks to in the entire in an entire traffic set, or want to look for all these sort of little file system and local log specific indicators. But even if we don't have that, we can kind of make inferences off just the relationships and how they connect over time. And so seeing these sort of rare paths sometimes is enough if we already have sort of the color coding and the asset information built into an analytic essentially. So it's kind of showing what I was trying to show at the high level with that high level graph picture. Is this is basically what we'll kind of pick out and label by the algorithm. And so kind of going back to here, that's really what I was trying to show at like a more granular level. This is what sort of the algorithm is hunting for, is just this sort of these strange paths essentially. And so I think we're kind of running low on time. Basically, that's sort of the end-to-end workflow, and more importantly, I think we just want to sort of deep dive on kind of where we use a lot of these data-driven techniques, and where kind of this is a good use case for machine learning, because it's much easier to get lots of labels for assets and stuff like that than it is for like attack patterns. And so that's just sort of like one of the many kind of ways we try to take signal from data and create sort of a kind of a good workflow that is useful for upstream, actually practical security, like questions. So maybe we'll just do Q&A next. Yeah.
Do you guys have any questions? Yeah, go ahead. Yes, the process usually goes, and I can translate this into what we just did at Black Hat. Basically, we grab a bunch of benign traffic, right? I basically simulated how a normal user will browse, right? And then we grabbed a number of pickups that had ransomware, right? So basically we trained the algorithm, and this is good, this is bad. And we included a number of what we call micro behaviors. So for example, the entropy in the URI string. We included things such as the MIME type sequence, right? And then going back to your question, at the end, we created a active defense script that basically grabs the executable that we're pulling from the pickup, grabs the executable name, SSH into a domain controller, creates a GPO by a PowerShell, and then pushes the GPO into the domain controller, right? Once you do that, it basically propagates. That executable will not run, right? And even if the numbers change, or the name, we'll still grab it and push it back again. So does that answer your question?
One other ancillary question is, you showed this WebServer example, but with WebServers, they have specific connections they're going to make. Why wouldn't you do a more whitelist approach instead of allowing them into your network border to allow to connect to arbitrary hosts? Because it seems like their customer someone on that network, on a laptop, should never be able to get instantiated a connection from that web server anyways.
Yes. Yeah, you're correct. Right. Well, it comes down to a customer, right? Some customers, I've been in customers that have, for example, east-west. You know what east-west means is lateral, right? So they kind of segment and divide their networks. And also north-south, so something like that will get blocked. Some others tell you, I can't do this, right? And what's scary sometimes is when you go to a customer and their guest, you see their guest wireless is actually flowing through the enterprise. So I show them things like, there's Tor here. Okay, you don't worry about Tor? No, that's the guest network, I don't care. Right? So yes, what you said is definitely valid, but it will depend. You know, when you're a customer, the customer presents challenges that you had to tackle regardless. I can tell them, hey, you got to fix your stuff because that's why I'm there for it. All right. Any other question? Yes, sir.
Yeah, essentially that's exactly the goal there. But see that we start with sort of some seed values. Like we start with what we know we want to hunt for. So the first sort of game to hunt for was basically monitoring like sort of some of these high risk perimeter assets, particularly web servers. And also like another great use case we get asked a lot is like, can you tell us when people are misusing and abusing databases? Well, oftentimes it's like, okay, do we have a non-exhaustive list of, oftentimes it's this sort of work in progress. So we're kind of let the data. I mean, it's great to get asset and inventory system, and we'll plug into that. But now it's kind of like the shadow IT problem a little bit we're trying to solve and discover what's the extra out there. And regardless what it is, we'll just kick off another analytic. So now that we know it's a web server, I can run the web show analytic. If I know it's a SQL server, I'll run sort of the SQL abuse analytic. And yeah, the way we've been building kind of a platform inside of Splunk that is sort of kind of exposes all these models as first-class citizens in it's called like a Lambda architecture. It kind of uses sort of a batch and a real-time paradigm to basically parallelize the problem across. We can assign state per entity in a parallelized way and maintain sort of a little local SAM per kind of individual. Oh yeah, and back to your question, like I just wanted to like highlight kind of that workflow. We have this active defense script. We didn't talk about this in this talk, but this was sort of our Black Hat demo. And active defense is a really interesting question, particularly in biomed, where I had to do this in healthcare. Like anytime people want to do automated blocking, it would be like, are you going to disrupt like critical life support? And so it was like a super like scary thing. But one of the cooler examples we've seen is this generation of GPO and just affecting policy. And oftentimes you don't have to take a really extreme action when you kind of do like a real-time risk score for a user. So taking maybe a first step, if the risk goes up enough, is just restricting subnets. Restricting subnet like access to critical subnets. And we've seen customers implement this on just heavy-duty engineering shops can implement this idea on a really interesting scale.
One other corollary.
Oh, sorry. I don't think I have them in this slide deck. I mean, typically we've been, we try to get like on average to be better than a coin flip. In this case, I think we were like in the 70% accuracy range for some of the samples we tested. But it's kind of like, oftentimes, some of the data, when we have to synthesize and localize it, it's not the same as the accuracy we'd see in another environment. So, but good question.
Yeah. Go ahead.
So a slightly different question. Do you correlate that with any of the metadata from configuration management solutions to correlate that the thing that was being configured and deployed to a server matches the fingerprint of what the server is currently serving, so that you can find out, like if an internal employee deploys an additional server binary across the server farm, but doesn't do it through configuration management, and be able to flag those types of anomalies to avoid incidents that are internal?
I don't think we've gotten a chance to use a configuration. Yeah.
I think the closest we got it was CyberArk, which was who's accessing what server and what scripts they have. That's the closest we had. As far as in order for us to do that, it is doable, but we will have to somehow tell the algorithm, right? I'll have to like I spoke before. I need to ETL that. You need to give me that in a format that I can feed it to Hadoop, and then the algorithm will process it and say, okay, this is normal. If I see something deployed by, so we had to build the logic and then we had to train it, then you can do it, yes. Yeah. Any other questions?
There's the link to that GitHub if you want the active defense tool.
Oh, here's the link to the tool that we released at Black Hat, and there is an active defense script there that will log into your domain controller and create a GPO via PowerShell. You can modify it and do anything you want with it. We'll plan to update it, and we're going to add ACLs, we're going to add SNORD rules. So hope you participate. It's open source. So if you don't have any other questions, then thank you very much.